Hi everyone. In this section we're going to talk about piecewise functions, which is basically when you don't see a single, for example, linear trend or quadratic trend. You see two or three or more different trends happening. So we're going to jump right into an example so you can see a little bit what I'm talking about. We're looking at a data set that's giving the temperature at various heights at a specific location. So we're looking to see what happens as our altitude increases, what happens to the temperature. And you can see that it does seem to follow a trend, but then the trend seems to change. So initially, the temperature is increasing very rapidly, and then the temperature starts increasing more slowly, and then the temperature increases a little bit more rapidly again. And I don't know exactly what's going on here. We are in kelvins. Typically, I would think that your temperature would decrease as your height increases, but maybe we're underwater, or who knows what's going on here. So I just think it's a really interesting shape to see in a data set. And what we want to do here is find a formula for the model that's shown with the dashed red line. So the dashed red line appears to be three different linear segments. So basically what I'm going to do is find an equation for each one of those linear segments, and then a piecewise function is basically just notation that groups those three pieces together into a single function and includes domain information about when each function applies. So I'm going to color code my work a little bit here. Let's start with this first piece. I'm going to color it dark blue. And we've got some points labeled that appear to be right about at the corners of these functions where they meet. So we'll use those 2 points. So 0, 288, and 200, 297. If we want to find the equation for a line, we're going to need a slope. So I will set up 297 minus 288 over 200 minus 0, which is just 200. So change in y over change in x. And I already calculated this. I got about 0.045 for that one. So that is the slope of my line. Let's pick some variables. I'm going to use h for height, and I'm going to use capital T for temperature. So for this first one, my temperature is going to equal 0.045 H, and then we need plus B, and in this case we actually were given B, so I think this will be the easiest one for us. The y-coordinate of the y-intercept is your B value, and we were given 0, 288 as our y-intercept. So there's piece number 1 that we will use. Piece number 2, that's going to be the shallowest piece in the middle. So now we'll use the points 200, 297, and 3,200, 299.5. So again, we'll want to calculate a slope. So I'll do 299.5 minus 297 all over 30,200 minus 200, so just 3,000. And this one, I got a smaller number, 0.00083. And since these are fairly messy, I think I'll use my point slope formula. So if you don't remember that one, it's y minus y1 equals m times x minus x1, where m is your slope and x1, y1 is any point on the graph. So I'm going to use the 200, 297 as my point. So I will say y, which is actually t for me, minus the y-coordinate, 297, equals the slope times x, which is h for us, minus 200. So we can add the 297 to both sides, and we can distribute. And I already pre-crunched so that it wouldn't be too long of you watching me do this. So I'll get the 0.00083H, and then when I do that distribute, 0.0083 times 200 times negative 200, and I add 297, just doing that arithmetic, I got 296.83. So just a little bit subtracted off, which makes sense. By the time we distribute that 0.0083 through, we're not going to have a very big number that's being subtracted. Okay, so that's piece number 2 of my equation. Piece number 3, this last segment, we'll use the 3,200, 299.5, and the 5,307. So again, we'll calculate a slope. And I got about 0.004, which seems pretty good. It should be smaller than the first slope and bigger than the second slope, and it is. So again, for this one, I think I'd use a point slope formula. You can use slope intercept as well, but similar to the last one, I'm going to use the 5,307, just so I don't have to rewrite that decimal. So 0.004 is my slope, and then h minus 5,000 this time. So once again, you'll distribute the 0.004 through, and you'll add the 307 to both sides. And my final result was that t equals 0.004h, and then from that I got 286.17. Okay, so those are the 3 pieces of my formula. Now what I need to do is put them all together. So I'm going to zoom in and draw this on the graph, see if I can make it all fit. Okay, so the notation for this is you use your function notation. We're writing temperature as a function of height. And then to group your 3 pieces together into a single function, you use a big squiggly bracket. So the first piece of my function was 0.045h plus 288. And that piece is valid for heights between 0 and 200. So we're looking back at our graph and saying that was only from 0 to 200, and this is a domain we're giving, so it should be x values, or in this case, h values. So we will either put in a comma, or you can write if 0 less than or equal to h less than or equal to 200. And here's one kind of funny thing. When the pieces meet, which is not a rule, sometimes the pieces don't actually touch each other, but when they do, it's impossible to say who should get an equal to and who should not. So I'm just going to group the 200 in with the first piece. It shouldn't matter because both functions are giving the same y value. So you just choose who gets that equal to. All right, piece number 2 was our 0.00083h plus 296.83. And that piece is valid for heights between 200 and 3,200. 200 less than h less than or equal to 3,200. And again, it doesn't matter which one gets the equal to and which one doesn't, but they shouldn't both. You shouldn't ever have to look at 2 different pieces of the function. So decide which one you're going to plug 200 into and stick with it. Either one is fine in this case. All right, last piece was 0.004h plus 286.17, and that is this final piece up here, and that was valid from 3,200 less than h less than or equal to 5,000. And you don't need a bracket on the end, it's just that first squiggly bracket that's needed. Again, those endpoints, the 200 and the 3,200, only one of them should get an equal to, but in this case it doesn't matter which one. That 5,000 should definitely get an equal to because it didn't show an open circle at the end of the graph. There's no reason for us to think that that should be excluded. So that is my final answer. You write down all 3 pieces, connect them with a squiggly bracket, give their domain restrictions. All right, thanks for watching.